Asymptotic notations. We did a lot of preparations. The main concept we introduced before we start this topic, the growth functions. The main thing we need to do, we want to compare growth functions. After we compare two growth functions, we want to describe the relationship between two growth functions in a compact way. Today we will do that. All right. D.1, introduction to asymptotic notations. First, we like to know why we need to use this kind of very special, very abstract notations, asymptotic notations. All right, so we look at the limits of two growth functions. Now, last time I gave you some examples. We compare, so we calculate the limits of the ratios of two growth functions. All right. Here, let us do some summary. Summary for those examples we did last time. In part B, part C, we did quiz questions. So part B, okay, all right. Limit of the ratio of two growth functions. When we consider that, what are the possibilities we may have? When we use the limit to compare two growth functions, we have these possible cases. We want to consider all the possible cases. Here, we summarize, we have these four cases. The first, the limit equals 0. When n goes to infinity, the limit equals to 0. Okay. Second, the limit equals some positive constant. Here, this c, although we can consider non-zero, but in our algorithm context, look at the underlying meaning of f of n, g of n, because we use these two functions to measure efficiency, right? And when we look at the efficiencies, we count the number of basic operations. Okay, so these two functions, we count the number of basic operations. So the underlying meaning is this, so we can assume the number should be positive. So for that background information, we can reasonably assume the C constant is a positive number, positive, real number. All right. The third case, infinity. And other than the above three, there is another case. It does not belong to any of the above three cases. We will see that. All right. So now discussion. For these four cases, we want to have some more discussion. For the first case, the limit equals 0, and we call the growth functions, right? We call f of n, g of n the growth functions because we use these functions to measure the growth rates of our efficiency functions. Yeah. All right. So then from the ratio, we want to compare which function grows faster, right? Yeah. So based on the limit results, we want to see the comparison results. Yeah. The comparison results should tell us which function grows faster. That information. So we need to give a conclusion. Yeah. Corresponding to case number 1, the ratio equals 0. Yeah. So you can see the denominator function grows faster, right? Yeah. Or you can use another way to express the meaning. The denominator function dominates the numerator function. Another way to represent dominates. Okay, yeah. Then we use a special term, order of growth concept. Order of growth concept. You know, if we use the order of growth concept, then our conclusion can be represented in this way. The order of growth of f of m is less than the order of growth of g of n. This way, the limit result can tell us this inequality result. Yeah. The inequality for what? For the comparison, for the order of growth of those two growth functions. Yeah. What we call order of growth? Yeah, you may wonder, why we call the concept, why when we measure how fast a growth function grows using this concept. Yeah, here, let me use a simple example to give you the idea, this order of growth idea a little bit. Yeah. Let us use some concrete example here. Yeah. This f of n, if I use a simple example n, yeah, just a simple n function. Yeah. And this g of n, let me use another simple function n squared. Okay, yeah. And definitely from the limit point of view, we have n over n squared, the limit equals 0, right? Yes. So matches our first case. Yeah. Then from the forms of these two functions, and this function, you can see both of these functions, they have the same form, n to the dth power. How about that? D is a positive number, okay? N to the dth power. Power function, yeah. They both in the form of a power function, okay? Yeah. When you compare two power functions, it's very easy, right? Yeah. So when we consider two power functions, n to the 8th power and n to the bth power, yeah, you can see easily, you just compare a and b, right? You just compare a and b. You can get idea quickly. Yeah, very convenient. The exponent numbers can tell us which one increases faster. Yeah. So here you can see in the polynomial or monomial. Yeah. So first, when the exponent number is an integer, it's a monomial, right? Monomial, polynomial, right? Yeah, it's that. And the exponent number corresponds to the degree of the monomial or polynomial, degree. Okay, yeah, all right. So that degree number tells us the basic information we need, or critical information we need. Okay, yeah, degree number. So that degree number, oh, actually, yeah. So here we use if we go back to the polynomial case, we use the degree concept in polynomial. All right, but for the polynomial, other than degree, there is another concept called order of the polynomial. Order of the polynomial. Yeah. So here, let me consider, a0 plus a1 n plus a2 n squared plus a3 n cubed. This case, all right. This is a cubic polynomial. Yeah. In this cubic polynomial, we say the degree equals 3, but there is another concept I didn't mention before. Yeah, here we have that. The order equals 4. Okay, order always equals degree plus 1. Degree plus 1. Yeah, that's the definition of order. Okay, yeah. So here you can see when we compare these two growth functions, basically we can compare their orders. Okay, orders. Yeah, because there is an original meaning for the order concept in polynomials. Yeah, but this order actually we extend from the polynomial order. Okay, the order, but we extend it. Yeah, why we extend it? Very simple. In the polynomial context, the order must be an integer, right? Must be a positive integer. Yeah, the smallest one is 1. The smallest order is 1 for a polynomial. Okay, yeah. 1, 2, 3 must be an integer. Yeah, but when we get to the growth function context, growth function not necessarily integer, right? Yeah. So our growth functions could be non-integer values. Yeah. So that's the reason we extend it. We allow the order of our growth functions to be non-integer positive numbers. Okay, yeah. So this D, only requirement is it's a positive number. Okay, yeah. So with this background, now you can see it is quite natural. We call order of growth of f of n and order of growth of g of n. And then that limit 0 tells us the order of the first one should be less than the order of growth of the second one. Okay, yeah. So that is the natural connection, yeah, between the limit view. Yeah. Here we take two views, the limit view and the order view, two different views. They are closely connected. Yeah. All right, so that's the case number 1. After you understand the case number 1, the remaining cases, yeah, we can understand just by analogy. Yeah. For case number 2, yeah, constant c, the limit, constant c, that c is a positive number. Yeah. So we can say both functions should have the same order of growth. Yeah, same order of growth. Yeah. So think about if the first one, you may have, let's say, 1/4 n squared. Okay. Yeah. The second one, you may have a n squared, right? Only their coefficient part different. 1/4 a, the numbers, the difference of these two numbers could be relatively big, but it doesn't matter. Yeah. Because the last time we cancel out that constant, right? So think about it. So last time when we consider f of 2n, the ratio over f of n, consider this ratio, that constant can be canceled out. Okay? Yeah. Yeah. So for that reason, even if these two constants are quite different, the difference is relatively big, but that's not important. When we consider order of growth, we ignore the constant part. Okay? Yep. We ignore the constant part. So we can safely say these two functions, they have the same order of growth. That's our case number 2. Okay? Yeah. So here, you need to adjust based on our background knowledge. You need to adjust the view to understand the relationship between two growth functions. Yeah, so that view is quite different from our usual view, usual comparison view. Yeah, our usual comparison view, these two functions, the difference is big, right? The difference is so big, all right? But in our algorithm view, if we ignore their constant coefficients, then they belong to the same category. So here we say they belong to the same category, n squared category. Okay? Yeah, same category. Then we put them together. Okay? So when we compare them, we say they have the same order of growth. Okay? Yeah. Yeah. So that's the, main adjustment we need to take in this order of growth comparison context. Okay. All right. Case number 3, similarly, the order of growth of f of n is greater than order of growth g of n. Okay. Yeah. All right. How about the case number 4? Yeah. The case number 4, why we have case number 4? You may wonder, right? Yeah. Because before I show you the detailed information for case number 4, can you imagine what is the possible case that belongs to, none of the previous 3 cases? Yeah. Because you may feel the first 3 cases should cover all the possibilities, right? You may feel in that way, but actually it's not. There is a possibility number 4, okay? That is, the limit does not exist. How do you know the limit exists, right? There is a possibility the limit does not exist. Okay, yeah. If you recall your calculus experience before, there is a possibility your limit does not exist. How about that? Okay, is that possible? Right? Yeah. But how to imagine, right? How to imagine Here, let me give you a simple example. The limit does not exist. Simple example here. All right. Let us consider these two simple functions. Okay, yeah. The numerator function, all right. Let me use 3 plus -1 to the nth times n squared. Okay. All right. The denominator function 4 minus -1 to the nth n squared. Okay. N squared can be canceled out. Yeah. But that ratio does not exist. Why does not exist? Yeah, because based on n even or odd, let's say n even first, when n equals to 0, that's even, right? 0, so that's 4, the numerator 4, denominator 3, okay? Yeah. When n equals odd, the numerator 2, right? Yeah, odd, 3 minus 1, so that's 2 over denominator 5, right? Yeah. 2, so you switch back to the previous pattern form, 4 over 3. Another time, alternatively, yeah, these two numbers change, alternatively, that's the pattern. When a sequence takes this special pattern, do you think the limit exists? It does not exist, right? Up and down, yeah. It never converges, yeah. So we say the sequence diverges, right? Diverges and not converges, okay? It does not converge, yeah. Diverges, yeah. In this way, the limit does not exist, all right? The limit does not exist. What does it tell us? Yeah. It tells us the limit way does not work for order of growth comparison in this way, all right? Yeah. But if we change to a different way, then probably we can get a comparison result. It just tells us the limit way does not work. It does not tell us there is no way we can do the comparison because we have other non-limit way to do the comparison. Yeah, we will see that later. All right. Now, the conclusion for this discussion. Okay. All right. Oh, yeah. So here, so here we need to use some compact notations. Yeah. Because look at here, case 1, 2, 3, 4. If our conclusions like what we did here, 1, 2, 3, 4, not that compact, right? We need to write a lot of words here. Yeah. But we want to have much more compact expressions that we need. The expression is, yeah, the first case, f of m belongs to little o of g of n. Little o. Yeah. Yeah. The special thing is little o. Okay. Now, what's the meaning? Yeah. Because the first time when you see it, you may ask, what's the meaning of that? The meaning is the limit of f of n over g of n equals to 0. That's the meaning. Okay. But we don't want to write in that, relatively more complex way, okay? We want to write in a relatively simple way, that this is the simple way. Yeah, okay? All right. If I use a little more words to explain this little o of g of n, that represent a set of functions, a set of functions. Okay, the meaning is a set of functions. What are those functions in this set? For all those functions, when you take the limit, one of those functions over g of function, you take the limit, that limit goes to 0. Okay, so you put all those functions in one set, and f of n belongs to that set. That's the meaning. That's the meaning. Here we use the set view. Yeah. Here in this expression, we use the set view. Okay, set view. Okay, yeah. All right. Similarly, for other cases, we have the similar notations. Second one, f of n belongs to big theta of g of n. Another set, this time, big theta of g of n, another set. Okay, yeah. The third case, f of n belongs to little omega of g of n. Little omega of g of n. Yeah. Okay. Here, these three notations, little o, big theta, little omega, these three notations, we call asymptotic notations. Okay, compact way to represent the relationship between two growth functions. All right, yeah. Now, that's the three of the asymptotic notations. We have a few more, okay, a few more. Yeah, all right. We will see a few more later. Yeah. All right. Yeah. But for case number 4, we cannot. So at this point, we cannot represent using the asymptotic notations. Yeah. Yeah. Because we do not have the comparison result. Okay. We do not have the comparison result. So we need to try a different way for comparison. Okay, yeah. So we need a new method for case number 4. Yeah. All right. So the new method, yeah, let's consider the new method using upper bounds and the lower bounds for the comparison. Okay. Objective. Even if the limit, this ratio does not exist, we can still compare two growth functions. Yeah. We just, get around that limit way. Yeah. All right. So how to do it? Yeah. The function g of n is usually a simple function like n squared, and log n. Yeah. It's natural, so why we use g of n usually a simple function? Yeah, because when we describe classes of growth functions, g of function, the one we use for the concise description, we want to use relatively simple functions as the, basic comparison functions. Okay, yeah. The function f of n could be a complex function. Yeah. All right. And then in this situation, how to find a reasonable way to measure f of n function, use some constant multiple of g of n to approximate f of n. F of n relatively complex, and the g of n very simple, but how do we represent a complex function in terms of a simple function? Yeah. So that's the objective. Yeah. So the way, use constant multiples of g of n. Yeah. Specifically, we try to find two positive constants, C1 and C2, such that C2 multiple of g of n less than equal to f of n, and less than equal to C1 times g of n. So here you can see from this inequality, we can describe f of n function, relatively more complex growth function, using two bounds, C2 times g of n, that's the lower bound, and C1 times g of n, the upper bound. So using upper bound and the lower bound, we can describe the range, approximate range for this f of n. How about that? Okay, yeah, that gives us an idea. All right, so you use f of n, so you have a growth function f of n, but when we compare it with the g of n, it is greater than C2 multiple, C2 constant coefficient, and the C1, it's less than C1 times g of n. We know C1, C2, they belong to the same category, right? Yeah. Belong to the same set of functions. What set? Big theta of g of n, right? Using our asymptotic notation from the previous slide, big theta of g of n. Yeah. Okay, yeah. So we get what we need. We get what we need, right? Yeah. Here, we do not use the limit way, right? We use the inequality way. Inequality way helps us to get around that limit way. And we eventually, we can find the information that f of n belongs to big theta of g of n. Okay, yeah, all right. So this method works no matter the limit of those two functions exists or not. Even if it exists, this method also works. Yeah. Even if the limit exists, this method also works. Okay, yeah, yeah. But the good thing for this method, when the limit method does not work, we can still use this inequality way. Okay, yeah. But one comment, yeah. If the limit way works, most of the times, the limit way is better. Yeah. Why? Because we can use the L'Hopital's rule. If the limit exists, then we can use the limit calculation techniques. We have many techniques to calculate the limits. Yeah. And those techniques could be very powerful. So we want to take advantage of those powerful techniques to calculate the limits. Okay? Yeah. So the limit way is pretty good. It has the advantage. Yeah. All right. Yeah. Yeah. All right. Next, define asymptotic notations. Yeah. Now, so based on our, understanding, this time, let us do formal definition of asymptotic notation. The first one, big O notation. Now, another notation, big O. Yeah. We have the little o notation, but this time big O notation. All right. Here, I give you the formal definition. Definition. For a given function g of n, the notation big O, we know it's a set, right? Yeah. From our understanding of the previous slide, it's a set. The big O of g of n, a set of functions represent, here, I said that, okay? The set of functions f of n that satisfy the following condition. There exists some positive constant c and some non-negative integer n0 such that this inequality f of n less than or equal to c times g of n holds for all n greater or equal to n0. So this is the complete definition of that big O notation. Yeah. All right. So from this formal definition, so here you can see, to understand it well, so we need to, really spend some time here. Okay. Yeah. Here you can see this little n, the n0, that's new. Okay, that's new. Yeah, we didn't use this little n0 before. In our limit way, we never use the notation of this little n0. Okay, yeah. And here, why you, in your formal definition, you introduce some new notation here. Yeah. Actually, this little n0, its role is important here. Yeah. It makes our understanding harder, but it's necessary. So we need it. Yeah. Here, let me spend some time to explain the role of this little n0. Okay, yeah. All right, yeah. So its role like this. Yeah. All right. Okay. So after you select it, so you have some freedom to select this number, okay, n0. So what is this n0? Yeah. You have freedom to choose n0. Okay, yeah. But after you select it, it must be fixed. This constant, it's a constant. This constant must be fixed where n grows. Yeah, because you can change the n value, right? Yeah, fixed when n increases. When you increase your n values, this n0 has no change. Okay, yeah, all right. And usually people use another way to represent this n greater or equal to some special n0 constant value. People say in this way, where n is sufficiently large. Another description for this n0 related condition, n is sufficiently large. In this expression, n0 does not appear. n0 does not appear. It's hidden. Yeah. So when you see this expression where n sufficiently large, you do not see n0 notation. Yeah. But it's hidden. N0 notation hidden. It means, yeah, there is some constant n0 where n greater or equal to that hidden constant n0, this inequality holds. Okay, sufficiently large. Yeah, because people may argue this sufficiently large, the wording is vague, right? Is the wording vague? Yeah. People can argue. So this wording is very vague. And sufficiently, when you use this word, it's not objective, right? Yeah. It's subjective. It's not objective. Okay? Because for different people, sufficiently large has different meanings, right? For different people, sufficiently large has different meanings. Yeah. Actually, not for different people, actually for different situations, the sufficiently large has different meanings. Yeah. Has different meanings. So later we will see the different meanings. The sufficiently large. Yeah. All right. So here, that's the understanding. Yeah. If I use the visual representation for this inequality, so you can see the graph like this. So this is the graph. Okay, graph. From this graph, you can see, yeah. We have the graph of C times G of function. Okay, yeah. We use as an upper bound for f of n, the curve of f of n. So this one. Okay, but that upper bound relationship only works when n greater or equal to 0. So when n is at the right hand side of the vertical line for n0. So this vertical line represents n equal to n0. At the right hand side, that means n greater than n0. Okay? Yeah. And how about the left hand side? It doesn't matter. So look at left hand side, this way, right? Yeah. Which one larger? It does not matter. It does not matter. Okay? Yeah. For this capital big O notation, the behavior for the left-hand side of this vertical line is not important. Why is that? Yeah. So here, we just raise the question. So why it is not important? Yeah. Here, let me delay a little bit. Yeah. Let me delay a little bit. Yeah, because if I explain the reason why it is not important, I need at least 10 minutes. Okay, so I couldn't complete my PowerPoint slides today. All right, but I will I will spend those 10-something minutes later to explain why it is not important. Okay, I just delay it. All right, but the concept is important. Yeah. I have to explain that why it is not important. Otherwise, you cannot get a good understanding of asymptotic notations. Okay, all right. Let's go to some other asymptotic notations, but this time we just use the similar way as our previous formal definition, but the change mainly is at the inequality way. All right, the definition for a given function f of n, the notation big omega of g of n represents the set of functions f of n that satisfy the following condition. Yeah, there exists some positive constant c and some non-negative integer n 0 such that only lower bound function representation f of n greater or equal to c times g of n function, big omega, okay, lower bound estimate for all n greater or equal to n 0. So here you can see the wording pretty much the same as the previous one. The only change is at the inequality side. Yeah. If you look at the graph, so you have the graph like this, but this time you do the lower bound estimate. You don't care about the upper bound estimate. Okay, you just describe the lower bound estimate. Okay, still this side doesn't matter. Okay, for the same reason. Yeah, later I just explain this reason once. Okay, once for all. Yeah, for all asymptotic notations. Yeah, so we explain this part why just once. Okay, yeah, because they have the same reason. Yeah, all right. Another one, big theta notation. Yeah, here we just change the inequality one. Yeah, the remaining, the wording pretty much the same as before. Yeah, standard. Yeah. All right. Yeah. Big O. Oh, sorry. Yeah. I realized I got something not quite right. Yeah. Sorry. Yeah. Yeah. I should know this. Something. Yeah, because this big O notation. Oh, okay. Yeah, that's fine. Yeah. So this big O notation, upper bound. Okay, good. Yeah. One side estimate. Yeah, from upper bound estimate. All right. Yeah. Then big omega notation, lower bound estimate. That's fine. Okay. Not wrong. Yeah, not wrong. But this big theta, both sides, yeah, quite natural. Both sides, we can estimate function f of n from both upper bound and the lower bound. Okay. Yeah. We see this kind of thing. We saw it before. All right. This time, if we use the graph visual way to represent it, we have both upper bound and the lower bound. Yeah. That's better than the previous two ways, right? The previous two ways, we only have one-sided estimate. Here, we have both side estimates. Yeah. So better than the previous two ways. Yeah. Yeah. All right. That's the formal definitions for three asymptotic notations. Yeah. All right. Yeah. Now after that, I like to give you some simple examples using asymptotic notations. Yeah, simple questions. Yeah. All right. The first question, show that n plus 2 belongs to the big theta of n. Show that. Okay. All right. Yeah. There are two ways to show. Yeah. Two different ways to show. Yeah. The limit way and inequality way. The limit way, actually, it's pretty simple, right? Yeah. The limit way, you just calculate the limit when n goes to infinity, numerator f of n, 2 plus n plus 2 over g of n, and after simplification equals 1 plus 2 over n, right? Yeah. When n goes to infinity, this 2 over n goes to 0, so the limit equals 1. It's a non-zero constant, or it's a positive constant. Okay? Then it tells us f of n belongs to big theta of g of n. That's the limit way. Okay, pretty simple, right? So it tells us when the limit of the ratio of those two functions exists, the limit way is better. Okay? Yeah. The limit way, so we can do it quickly. Okay? But here I like to do practice on that inequality way. Inequality way, if we work on the simple example, what should we do in inequality way? Let me show you. Because big theta, you need to consider both upper bound and lower bound, all right, to estimate this main function n plus 2. First, let's look at the lower bound. What constant multiple of n can we use as the lower bound of n plus 2? That constant we need to know here. How about that constant 1? 1 times n, just n. We know n always less than n plus 2, right? That's trivial, okay? That's trivial, and always less than n plus 2, no matter what, okay? Yeah. Here because remember, in our formal definition, we have an n0 notation concept. So that is n0. So when we write this inequality, we need to specify n0 explicitly, okay? Because we need to use it later. So we need to write it out, n0, for later usage. Okay, all right. It tells us C2 equals 1. Yeah, our lower bound constant C2. Okay, then the upper bound constant. Now, for the upper bound, it is a little slightly harder, yeah, but still pretty simple. The question is, what constant multiple of n you can use to be the upper bound that is greater or equal to n plus 2. Okay, yeah. Remember, you're allowed to use that little n0. That little n0 is useful here. Yeah. All right. How about you just replace 2 by n to make it larger? The first term n, you keep it. The second term 2, you enlarge it to n, because we know usually n should be greater or equal to 2, right? Yeah, but n could be less than 2. When n equals 1, it is less than 2. But remember, we have the n0 thing that plays important role here, because we can skip some values of n, those values that we can skip, they are covered by n0. That's the important role you can see here. So when n greater or equal to 2, we can say our n plus 2 less than or equal to 2. Yeah. Here, at that time, you can see we just let n0 equals 2. All right? Yeah. Yeah. So here you can see when we use the n0 concept, we put things under control, right? We put things under control, right? Yeah. All right, so now we have both constant, multiple constants, C1, C2 values. Yeah. Other than that, we need to choose a good n0 value, all right? N0, when you have the first one, 0, these two should be both true. These two cases should both, sorry, what I mean, n greater or equal to n0 covers both cases. Okay, yeah. So we should choose the larger n0. Okay, larger n0, saying then it covers the both cases, not the smaller n0 value. Okay, yeah, because the larger one, if it is true, definitely n greater or equal to the smaller one, right? Yeah. So what after this much work, we make our conclusion. It is true. That is our conclusion. Okay, so you can see you need to do this much work. Without using the limit way, you need to do this much work. If you compare these two ways, the limit way, inequality way, you can see limit way is easier, right? Yeah. Inequality way, you need to do a little more work. Yeah. All right. Let's look at example number 2. Yeah. This time, we only need to do one-sided estimate. N cubed greater or equal to some constant multiple of n0, but that's easy. The constant, we just choose 1. Okay. And n0, this is the n0, yeah. N0 equals 0. Okay. The constant C equals 1. Yeah. Then we are done. Yeah. Yeah. This case, the limit way, yeah, the limit way is not limit way. The inequality way is simple. The inequality way is simple. Yeah, but here the question, yeah, right. Yeah. How about the limit way, right? How about the limit way? Okay. Yeah. How about the limit way? Yes. Yeah. The question. Yeah. The answer. No limit way for this case. Yeah. Actually, yeah, the reason, yeah. Yeah, because yeah. Yeah. Or so although so no straight, yeah, so here it should be So the limit way, yeah, because when you consider limit way, you need to be very careful. All right, yeah, be careful using the limit way. All right. Yeah. Okay. Yeah. So you need to, so when you use the limit way, when you make your conclusion, you should be very careful. Okay. Yeah. You should be very careful. Yeah. So you can use the limit way to help you get some information, but when you make conclusion, yeah, you need to be, very careful. Yeah. But usually, for this way, we just use the inequality way. Okay. Inequality way. Yeah. All right. All right. How much time? Yeah. All right. So let me try another examples before the end of class. 2.3, next question. This time, n plus 2 cube belongs to big theta of n cube. Yeah. Here, if you use the limit way, that's simple, right? Limit way, the ratio of these two functions yeah. We just consider cube n plus 2 over n. Okay, yeah. And after simplification, 1 plus 2 over n cube, we know this expression 2 over n goes to 0, where n goes to infinity. So that is 1 cube, that's 1. Yeah. Limit way, very simple. Okay, so you get a conclusion. But let's practice the inequality way another time. Lower bound and upper bound. Yeah. Our targeting function n plus 2 parenthesis cube. Okay. Lower bound, easy, just n cube. We drop that 2. Okay. And this inequality holds for n greater or equal to n0. So this is our n0 constant. Okay, all right. Then for the upper bound, similar to our 2.1 example, okay, yeah. All right, C2 equals 1. We replace n plus 2 by n plus n, and we know in this case, our n0 equals 2. Okay, yeah. So we have the 2n expression, larger expression, yeah, for n plus 2, and then we raise the power of 2n cube power. So that's a times n cube. So we get the upper bound constant C1 equals 8. Yeah. Here, I like to mention some, some problem I saw from my students' work before. Okay, yeah. Many students, when they work on this question, they did in this way. They expand this n plus 2 polynomial. Okay, yeah. So the expansion like this, n cubed plus the formula 3 times n squared times 2, that's 6n squared plus 3 times m times 2 squared. So that's 12m plus 2 cube. That's 8. Yeah. After they get this expansion, then they try to find some constant multiple c times, yeah, how hard it is. Yeah. So then they try very hard to try to find that c. Okay. Yeah. Yeah. But so many students use that way, this way, expansion way. Yeah. Here you can see if you do not do that expansion this way, much easier, right? Yeah. So you get constant multiple inside that parenthesis. Yeah. After you get constant multiple for the base part inside parenthesis, then you raise to the certain number power, much easier. Okay, no expansion. Because think about, sometimes I ask those students to estimate plus 2 to the 5th power. Then how long is the expansion? Think about, okay? Yeah, 5th. Although not too long, think about when the exponent number becomes larger and larger, why you need to write the whole expansion out, right? Yeah, you can avoid that, okay? Yeah, so here, the suggestion, try to avoid that expansion way, okay? That tedious, tedious work, expansion way, yeah, all right, yeah, so that's the comment, yeah. Although, yeah, here, I have example number 4, yeah, but, so this one, little o, so it's better we use the limit way. So here, I have 2 minutes, yeah, because we did this work before, so we can quickly complete it. So we do not need to come back to the slide later, yeah, all right. So here, when we use the limit way, the L'Hopital's rule, remember the last time we need to do the rigorous math, right? But here, n is a discrete variable. So we should switch to the continuous variable version. All right. For the continuous variable, then the definition of derivatives exists. Okay. Yeah. Yeah. All right. So log, the base is hidden, but in our context, in our algorithm context here, yeah, because we have a context, right? So in the algorithms context, we have this, okay? Yeah. In the usual math context, we may not have this, yeah, but in our algorithm concept, we can safely say we can make this assumption, okay? All right, so then apply the L'Hopital's rule. Why we can apply L'Hopital's rule? Because it is the, yeah, let me just recall, because we have infinity over infinity indeterminate form, okay? Yeah, so in your mind, you need to check this, yeah. Although in my math formula, I didn't write it, but at least in your mind, you should be aware of it. Indeterminate form. Then you can take the derivative in this way. So after simplification, you get the answer, the limit equals 0, and your conclusion is little o notation. Okay, yeah. And you can switch back to the discrete variable. Okay, yeah. All right, so that's the, everything we need